Yeah.
This is really
All right, so let's get started for the second ALS lecture of the year. So before introducing our speaker, let me remind you that we're recording the lecture, so I would appreciate if you could turn your cell phone off. It's my great pleasure to introduce Professor Jenann Ismael, who is now professor at Columbia University, after having been a professor at Stanford for a short period of time and professor at the University of Arizona for a longer period of time. She got her PhD at Princeton with Basfriend Frassen, who was her advisor, and Jenann works on a range of topics, but with two main areas of research. One is the philosophy of physics, and I guess the talk today will be more in that tradition. But she has also done some important work in the philosophy of cognitive science, and her penultimate book was on situated cognition, and really an excellent book. She has published 3 books, and I will only mention the last 2 ones. The Situated Self, the one in the philosophy of cognitive science, which I highly recommend. Actually, it's a wonderful original book, published in 2007 with OUP. And the last one, which was actually widely discussed and actually had a really a broad audience, is How Physics Makes Us Free, published in 2016 with OUP, and really a remarkable book, extremely interesting, extremely written. If you haven't read it, I highly recommend it. And she has published tons of papers, but I don't want to spend the next hour going through her very long CV, and she won many prizes, as you can imagine. So it's my pleasure today to introduce Jenann Ismael, who's going to be talking about what does it all mean, some questions about totality.
First, thanks so much for having me and for all showing up on this sort of gloomy day. I'm going to the talk is going to have a sort of dramatic arc. So what I'm going to do is I'm going to start by talking about a little puzzle. So at least a couple of you have heard me talk about the puzzle before, but that's actually going to be a kind of prelude. So I'm going to introduce the solution to the puzzle, or the resolution or the dissolution of the puzzle, and then suggest that actually uncovers something deeper and more interesting. And I'm going to spend the rest of the time talking about the deeper and more interesting thing. And when I say I'm raising questions about it, I really mean that I'm raising questions about it. So the little puzzle is something that I started thinking about a while ago, and it goes something like this. I'm going to introduce it very quickly. You're going to have all kinds of questions. You can raise those at the end, but actually this is just the build-up, so don't worry too much don't get distracted by them. It's convenient to have something concrete to focus on, I think, to motivate the rest of it. Okay, so consider the simplest and most straightforward example of a deterministic theory, Newtonian Mechanics, and consider Laplace's famous demon, or superintelligence, that has knowledge of the laws of nature and knowledge of the positions and the momenta of each of the particles of which the universe is made, and this superintelligence has the ability to calculate as fast and as accurately as you please. And now consider the fact that the Newtonian laws are pretty trivially compatible with the construction of a little thing that I'm going to call a counter-predictive device, and the thing is designed to undermine any revealed prediction of its behavior. So here's how the device works. It's just a little machine. Maybe it has a red light and a green light on top, and in any given sort of run of what I'm going to call an experiment, it takes as input a prediction of what it's going to do, whether it's going to flash red or green, and it does the opposite. Okay, so it flashes red if it's predicted that it will flash green, and green if it's predicted that it will flash red, or it'll do nothing. Okay. Or maybe it's a more complicated machine, like the one on the right, but the complexity doesn't make a difference. Okay. So now, if we put this sort of machine into communication with this Laplacian superintelligence, giving it knowledge of the laws and the positions and the momenta of each of the particles of which the universe is made, and as much computational power and time as it needs to make its calculation. And then we ask it to give its prediction, to feed its prediction into the device in a form that the device recognizes. So for the thing on the left, it's going to be a limited number of forms. For the thing on the right, potentially indefinite number of forms. And then we see what happens. Okay? And it looks like this that this setup is what we've done is constructed effectively a self-defeating causal chain. So here's how that goes. If A is the name of the outcome of a counter-predictive experiment, A occurs if the laws and initial conditions logically entail A. That's just because we're in a deterministic context. The laws and initial conditions entail A causes the Laplacian intelligence to predict A. Laplacian intelligence predicts A, then the counter-predictive device runs through its runs the causal procedure, and the counter-predictive device performs not A. It looks like that's what we've set up. And this is not just a thought experiment. It's interesting because it's a physical situation that could, in principle, be physically implementable in a Newtonian setting. So if you sensed a connection to puzzles that arise in connection with closed causal loops, you were right. Since information about the total state of the world at any past time in a deterministic context is information about the future. What we're doing here is we're creating a situation in which we effectively feed information about the future into the causal past of a system that's designed to undermine it. So self-defeating causal chains, they don't immediately lead to contradiction, right? For the same reason that the puzzles that arise in connection with closed time-like curves aren't genuine paradoxes. There are consistent global solutions, but what is usually accepted to be the case, I can argue for this if you want, but that it's not the case that any local solution to the laws in general can be extended into a global solution. So there are consistent solutions, but there's restrictions on the initial conditions. Not any old set of data along an initial boundary surface can be extended to a global solution. Now, in the context of closed time-like curves, certainly those restrictions on initial conditions go against our expectations, but it's not a surprise in that setting that closed time-like curves introduce pathologies that go against our expectations. It would be surprising to find the need for this kind of a restriction in the deterministic setting on a flat space-time. So that's the puzzle. And indeed, the fact that determinism is a formal consequence of local laws that place no such restrictions on initial conditions should signal that there was something wrong in the setup of the counter-predictive, of this purportedly self-defeating causal chain, Laplacian demian plus counter-predictive device. Okay. And indeed, that's what emerges sort of when you look a little more closely at whether this chain is in fact implementable, the self-defeating causal chain. So although the puzzle, as I've set it up, is put in terms of what's possible for Laplacian intelligence to know, it's not really about knowledge. All that the Laplacian daemon is doing is sort of acting as a causal intermediary that hooks up facts that are, by hypothesis, nomologically sufficient as a matter of law, to fix the entire future of the world, and in particular to determine the output of the device to something that leads causally to the opposite of what is predicted. So it seemed like, right, in a deterministic context, there have to be events in place already at some past time that are sufficient as a matter of physical law to fix the future. But it also seems like we have the sort of causal freedom to attach whatever kind of causal chain we like at any given moment to whatever facts are already in place, and we're just exploiting that by sort of inserting this counter-predictive device to get causal chains that seem to lead to opposite conclusions. So whatever those facts entail, it seems, why wouldn't it be possible to add something that would undermine what they're supposed to purportedly fix in the future? So, and I think when it's put this way, the puzzle actually dissipates because it turns out not to be true in a deterministic context that there are events in place that are nomologically sufficient to fix the future. And here's why that's so. Let's start with a simple case. So we'll start with a deterministic Newtonian universe. Consider the history of the universe. I meant to do that, and now we're here. Okay. So consider a deterministic Newtonian universe and consider the history of the universe up until sometime t. And an event that occurs just a fraction of a second after t, and ask, do the events that make up the history of the world up until t nomologically determine E, this event a fraction of a second later? And the answer is no, and the reason is that we just have to add things to C, to the set of events up until t. We just have to add something that change the forces impinging on E, and then something else will happen. And that's quite general. There is no intrinsic nomological connection between the events in C, that is a collection of events up until time t, and anything that happens later. For any collection of pre-t events, there are models of the Newtonian equation of motion that include those events in which E, and models of the Newtonian equations of motion that include those events and E doesn't happen. And you might think here that the problem is that there is no way of prescribing events in Newtonian context that are nomologically sufficient to determine E. And for reasons related to this, it's usually thought that Minkowski spacetime is a much more hospitable environment for determinism, because in Minkowski spacetime we can prescribe the set of events explicitly that are nomologically sufficient to determine a given event. So in Minkowski spacetime, of course, the only structure is the light cone structure. The events in E's past light cone, right? Or the set of events along some cross-section of E's past light cone determine E. But if E lies at some finite fraction of a second in the future from here now, then nothing in E's past light cone, nothing in my past light cone from here now, that is nothing that's already in place from the earlier perspective, nomologically determines E. There are always influences that are outside my present causal horizon, but relevant to any event that lies at a finite temporal interval from here now. What happens at that time hinges on what happens between now and then, and in general that can be anything. Okay. So if we're trying to express the worry that determinism entails that there are facts already in place at any given moment in the history of the universe, that nomologically determine the future, whereby that would mean something at a finite temporal interval from now, it's simply not true that in Minkowski spacetime, again the most hospitable setting for determinism, that's so. What counts as already in place is the causal past, and there's no good sense in which the events in the absolute elsewhere that would need to be included in order to determine an event in the future are any more fixed than the future itself. The causal, that's why the puzzle is not really a causal puzzle. The causal doesn't generate sort of self-defeating causal chain, because the causal past does not, in fact, nomologically suffice to fix something at any time in the future. So the causal part of the puzzle is dissipated. Determinism by itself doesn't give rise to the possibility of self-defeating causal chains, either in a Newtonian or a Minkowski setting, nor in general relativity, but general relativity has never been a hospitable home for determinism for other reasons. And I'll say a little bit more about that below. Okay. So again, there aren't facts in place that are nomologically sufficient to fix the future. You can always defeat the nomological connection between past of here now and events in the future by just adding more stuff. But now that's just the beginning of the story. Because if we ask, what would a Laplacian intelligence have to know in order to predict the future? It's not just that this particular set of events that occurred, or not that there were these particles with these positions and momenta at some past time, but that those events, or those particles, exhaust the totality of what there is. So if we fix the contents of the absolute past and the local form of the laws, and we ask what will happen tomorrow, there's an indefinite number of possibilities, an indefinite number of solutions to Newtonian equations of motion that include those things in which very different things happen tomorrow. And if we add something that fixes the total state of the world at any past time, we wipe out all of those possibilities except for one. So the question is, why would that be so? What facts about our world fix its total state? And when is that state fixed? When do we go from this sort of plurality of possibilities down to just one? And I think this is the deeper and the more interesting question that I mentioned. It sort of opens up a whole cluster of interesting questions that go beyond significance just for understanding determinism. And so that's what I'm going to spend most of the time raising questions about the logic and the metaphysics of totality, and then show how they're connected to interesting issues in physics. So, and then to make a kind of provocative suggestion at the end that I think nudges everything into the right set of relationships. I actually I don't expect you to believe the provocative suggestion. And I think I'm more interested in seeing like what you think about this whole cluster of issues, which seem to me sort of fascinating and unsettling to customary ways of thinking, certainly unsettling to the ways that I had grown accustomed to thinking and been taught to think. And they're much more in the wheelhouse of at least some of you here than my own, so I'm sort of selfishly interested in getting people talking about them and seeing whether there's a natural way to understand all of this that gets rid of the puzzling aspects. It's always my favorite kind of talk, is where you go away with interesting questions that you hadn't thought about rather than being told what to think. So if one looks at the logic of claims about totality, they're connected to universal quantification because the domain of a universally quantified sentence, all swans are white, is totality. The quantifier in a claim, like all swans are white, ranges over everything, not everything in some specified class, not everything in some restricted domain, but absolutely everything. And universally quantified sentences, of course, are logically equivalent to negative existentials. So to say all swans are white is to say that there are no black swans. So these three things, claims about totality, universally quantified sentences, and negative existentials, are largely interchangeable. Reasons to worry about one are reasons to worry about the others, and connections between them, I think, sort of help illuminate one another. So at first, the notion of totality seems utterly mundane. If we think about the eggs in a basket, for example, we all know what it means to say that for any particular egg to be in the basket or not in the basket. We can have effective procedures for determining whether any given egg is in the basket. But this doesn't give us an effective procedure for determining the total number of eggs in a basket. And we all know what it means to say that there's a total of 6 eggs in the basket. That means that there are 6 eggs in a basket and no more. But now think about that crucial phrase, and no more. There are not, in general, any logical or nomological connections between there being 6 eggs in the basket and there being no more. And in general, there's no way of establishing an and no more clause by examining elements in an unrestricted domain. If a domain has boundaries, then there is something that counts as having done a complete search. And you get to the point at which all opportunities for contributing to the total have been exhausted. The problem is specifically with a statement about the total number in an unrestricted domain. In general, whatever your atomic facts are, there is no logical or metaphysical entailment between a body of atomic facts and a totality statement. That's what it means for them to be atomic. There's no necessary connections between them. Without such a limitation, there is no way of going from each to all, or to there are none that are not, or to a statement about the total. No body of first-order facts on its own establishes a universal quantification, something all of the form all x's are f. And no body of first-order atomic facts establishes a negative existential, no x's are g's, and no body of first-order atomic facts establishes a claim about the total number of anything in an unrestricted domain. We can make easy sense of the total number of eggs in a basket or the total number of Republicans in Congress going down because those are domains whose boundaries are given. When the boundaries are given, again, there's something definite that counts as making a complete survey of its contents. And in first-order logic, I think we're always given a domain, a universe of discourse, and then we go on to associate truth conditions with the quantifiers. We say, here is the universe of discourse. We explicitly specify all the things that there are, all the things that are possible, that can make a possible positive or negative contribution to the total. And that specification creates an inferential bridge between a set of atomic facts, this is P, this is P, this is P, to universal quantification, all things are P. Or there are none that are not. But there's no logical rule that takes you from a collection of atomic facts to universal quantification. And that is because there is no logical rule that takes you from a collection of atomic facts to a negative existential. Again, nothing in adding positive instances rules out there being more. What it means for these, again, to be logically atomic elements is that you can always add more as a kind of logical and metaphysical, on a logical and metaphysical reading of can. The difficulty comes up also in metaphysics. So a good part of metaphysics is concerned with saying what there is and with formulating principles that relate some sort of base ontology to higher level objects and a wider ontology that includes complex objects and so on. Okay? So often these days, the base ontology is taken from physics. The central principles of the program in the metaphysics literature are these. So I'm not endorsing any of these principles. I think they're a convenient way of also bringing out the same problem. So there's the truth maker principle. Collection of entities makes a proposition true if and only if their existence necessitates its true. The grounding principle, anytime T in any world W, if P is grounded in C at T and W, then P is necessitated by C. And Humean supervenience, if two worlds, if W and W prime are any worlds that are duplicates with respect to which fundamental facts obtain, then W and W star are duplicates with respect to which facts obtain simpliciter. Okay? Each of these principles runs into trouble with totality facts for something like the reasons that we've been saying. So consider a world in which there's a total of 2 billion people and ask what makes it true that there's a total of 2 billion people at the world. What grounds the number of people in that world? Well, it's not the people in that world. Okay? There is nothing about those people that keeps them from being part of a world with more people. And it doesn't help to look more widely in the world because you can take W with all of its people and all of their relations to one another and everything else intrinsically fixed and embedded in a world with more people. That also means whatever makes it true that the number of people, that there are 2 billion people in W doesn't supervene on facts about the people in W or indeed about anything internal to W at all. The unrestricted totality facts in general are not, at least according to these principles, grounded by anything in our world. They're not made true by anything in our world, and they don't supervene on anything in our world. So the space-time analog of the idea that no matter how many you've examined, there could always be more, is that no matter how large a volume of space-time you consider, there might be more. No matter how large a volume of space-time you consider, it can be embedded in a still larger volume. We could also do things in terms of particles or fields. It doesn't matter how many particles there are, we could always add more. No matter how far the field extends, we can always extend it farther. Whatever your fundamental ontology, the suggestion is that there's a version of this, we can always add more. And the interesting thing for physics is that the can here can be understood as meaning not just as a matter of logical or metaphysical necessity, but but even can as a matter of physical law. And the way to gauge that, whether we can add more in this sense, is whether given any model of the laws, there is a model that embeds it as a proper part, that a model that embeds it and has more in the relevant sense. So we saw that if we just stay at the level of describing nomological connections between particular events or the events contained in specified volumes of space-time, then an event that falls at even a finite fraction of a second in the future of a point P, even in Minkowski space-time, again, the most hospitable setting for determinism, is not in fact fixed by the events that fall in P's past. And this is not just the epistemic point that a creature in space and time who's confined to knowledge of its own causal past is never in a position to have knowledge of the laws to calculate what happens in its causal future. It's the much more interesting point that there's never enough information contained in its past to nomologically fix events at even a fraction of a second into the future. So it was easy to see, in Newtonian space-time and in Minkowski space-time that you can defeat the nomological connection between any given past and any specified future by adding stuff along the sides, so to speak, stuff in the absolute elsewhere in Minkowski space-time or stuff just along the sides, along a space like along a time slice in Newtonian space-time. But what about general relativity? So things are more complex here. In Newtonian mechanics and special relativity, space-time is the fixed background against which matter moves. The progression from Newtonian mechanics to special relativity brought the geometry more in line with the causal structure, but it remained true that you could add to the material contents of the universe and arrange it however you like without affecting the geometry. In general relativity, of course, that's no longer so. The field equations relate the geometry to the matter content, so it's no longer true that you can add as much matter as you like and arrange it without affecting the geometry. The local structure is still Minkowskian, but there's a wide variety of possible global structures, and there's a more pronounced and well-studied division between the local and the global structure. Okay? And when I talk about local structure here, it can be very generous in what we mean by local. Okay? Local, for our purposes, means internal to the world. Local structure is structure that's intrinsic to or determined by facts that are intrinsic to some specifiable volume of space-time. So something that you could find out by investigating some specified volume of space-time inside the world. Global structure is structure that characterizes the universe specifically as a totality. Global structure includes things like whether space is finite or infinite, whether there are singularities, whether space-time is hole-free, whether there are closed time-like curves, whether there are Cauchy surfaces, and which particular surfaces are Cauchy. If we look at what the theory itself tells us about how global structure, in this sense, is constrained by local structure, it turns out that something very like what we said above about Minkowski and Newtonian space-time is true. So there's a theorem conjectured by Malamant and proved by Manchak that says consider two spacetimes n and m primed. We could say that one is observationally indistinguishable for the other if for every point in the former there's a point in the latter whose causal past is isometric. So given a spacetime m, given that a spacetime m GAB is observationally indistinguishable from another m prime GAB G primed AB. An observer at any point in the first cannot know which of those two it is in. Okay. Now the theorem is, let M GAB be any space-time satisfying any set C of purely local conditions, and it's important here that the field equations are local. There exists another space-time, one that is not isometric to the first, such that the second satisfies a set of local conditions and is observationally indistinguishable from the first. So here's the argument sketch that Malamant gave. It's been called the clothesline construction. It goes something like this, and this was just a conjecture when Malamud suggested it. Let the PIs be a countable sequence of points whose causal paths exhaust the totality of M. Then, like a clothesline, it seems that we should be able to take the causal paths of those points, string them out with an appropriately chosen space-time filler, that's the version adding more, such that they would be isometrically embedded disjointly in some other space-time that was also a solution of the laws. Okay. Space-time filler in between the embedded causal paths of the different PIs that we chose is subject only to the constraint that the metric be smooth. So with great flexibility, it seems like it should be possible to choose the filler so that the second is not isometric to the first. But because of the way that the thing was constructed, every point in the second would have a causal path that was isometrically embedded in the first. So it would be observationally indistinguishable from the first. Intuitively, the idea is that we can lay out a collection of causal paths in a general relativistic space-time, adding things in between to yield another that was also a solution of the laws. That was the idea. Manchak proved it, and what this means is that there's a kind of generalization of what we said before to the general relativistic case. Take the causal paths of any collection of points in space-time that covers the whole manifold. There's always a solution to the laws that embeds those in a model with more stuff. The model with more stuff has a different total state, different global properties, and also a different future. And that, in its turn, means that the causal path of a general relativistic spacetime does not fix either its global geometry or the total state of the universe. So again, this seems to mean that nothing in what is already in place, logically, metaphysically, or nomologically, rules out there being more. So nothing that's already in place that fixes or grounds totality facts as a matter of logical or nomological necessity. Okay, the total state is determined by the matter content, but never yet by anything that is already in place. Never by the causal paths of any collection of points that you care to choose. So, at this stage you should be puzzled. I think we've been having trouble, or I've been having trouble, or suggesting that it's at least puzzling, forming a clear and distinctive idea of what totality is supposed to be. That is, what these totality facts that pertain to the world out specifically as a totality, what their truth makers are, what they are facts about. And maybe it's not an accident that we're having difficulty here. Maybe there is no such thing as totality. And those are people that have said things like this. Okay. And I don't mean here restricted totalities, like the totality of eggs in a basket. I mean no such thing as the true or absolute totality. The most obvious reason, the most obvious motivation for saying something like that is avoidance of the set theoretical paradoxes. A slightly more nuanced motivation is reflection on what the set theoretical paradoxes teach us about how language works. At a bare minimum, the set theoretical paradoxes teach us that certain types of apparently apparently describable totalities are not well defined. So there's no totality of all sets, no totality of all ordinal numbers, no totality of people shaped by Russell's famous barber. Okay? And that means that we can't use the notion of totality naively. We can't rely on the presumption that every syntactically well-formed description of a set refers to something that actually exists. I actually think there's a lot more to say about this. All I'm going to say about it now is that at least it suggests that the burden falls on someone that wants to use the notion of totality to specify what exactly they're talking about. And what we've been seeing is that, at least in this case, no explicit definition is possible. No list of events, no identification with a specified volume of space-time, is going to work. We might try to define absolute totality as the limit of a procedure, starting with some particular portion of reality that we can draw boundaries around. We imagine that we can just keep taking bigger and bigger chunks of reality, moving the boundary between inside and outside farther and farther out until we've included everything, but that doesn't work either. However big we get, it's always possible to add something to it to obtain a more inclusive totality, either by extending it along the sides or by a clothesline construction in general relativity. So what would be the implications for physics if we did decide just not to talk about totality? What would the physics of the on-the-ground causal structure look like? What if we simply denied that there was such a thing as totality? What if all there ever is the totality of things so far, or the totality of things that we've counted, or the totality of things in some specified volume of space-time, but no absolute totality? For one thing, if there is no totality, there is no determinism. All nomological connections between specifiable volumes of space-time in the past and anything that lies at a finite interval in the future is conditional. Conditional on what happens in between, and again, that can be almost anything. Determinism is what we get by taking sort of bigger and bigger chunks of reality until we've made everything endogenous. But the point of the above is that we never actually arrive at the deterministic limit. In every example of a deterministic theory that's been taken seriously as a theory for our universe in physics, and in our best current cosmological theory, no matter how much time has passed, there are no nomological constraints on extending the universe along the sides or into the future or by clotheslining in additional volumes. Totality is something that is, in this sense, perpetually deferred, never achieved. The deterministic case is uninteresting because that deterministic case is degenerate. Okay. Now, I'm not endorsing any, I'm taking you through a line of reasoning that's pointing in one direction and seeing what the implications are. So that sounds pompously metaphysical, but it's motivated by a very simple thought. If you invite people to enroll in a class that you're teaching, normally there's a time limit or there's a cap on the size of the class. The total enrollment is achieved once all of the potential enrollees, all first-year majors, say, or all enrolled freshmen, or all students in the year that the class is offered. Once they've registered their decision, then the total number has been achieved. Right? And in general, we think that a total is achieved, the total positive votes in an election, the total hours of sleep in a lifetime, when all opportunities to contribute to the total have been exhausted. But what if the class is online and ongoing? What if students can enroll at will in an open-ended way, and there's no limit to the pool of students, and there's no particular time at which the class is proclaimed to be filled? Right? In that case, we can talk about the total number in a given year, the total number over a given time period, but there's no such thing as the total number of students in the class in absolute terms. That is simply not a well-defined class. We could go on waiting forever without exhausting potential contributions to it. That's the thought. The problem is not that the enrollment in such a class would be infinite. I have no doubt that at any time we took a tally, the enrollment would be finite. The enrollment might never, in fact, get over 1 or 2. The problem is that the enrollment is open-ended. The problem is that there's unlimited potential for for additional enrollments. The total number is what we get at the full and final accounting, and there is no such thing in this case, nothing that counts definitely as having made a full and final accounting. Literally no time at which the full and final accounting can be made. The person who talks about the total energy of the universe, the suggestion is, might as well be talking about the total number of students in a never-ending online, unrestricted class. Totalities of this kind are literally never achieved. Okay. On the other hand, we all know what it means to say that there are these things and no more. And when we want to study the physics of totalities, we put a particular collection of things into interaction, we specify that they exhaust all that there is, and we look at the emergent physics. We know how to write down Hamiltonians and see how they evolve. Doing so plays an important part in physics. It helps us understand what a set of laws entail about what kinds of worlds are possible. Making totalities objects of formal attention can reveal symmetries and conservation principles. This sort of exploration plays an essential role in discovery. Looking at the physics of restricted totalities that can be explicitly specified gives us deeper insights into the laws. And of course, there's cosmology. If we look back at sort of before early last century, people practiced cosmology mostly as a sort of study of large extraterrestrial planets systems like planets and solar systems. It was really Einstein's 1917 paper, Cosmological Considerations on the General Theory of Relativity, that changed all of that, transforming cosmology into a science that's specifically devoted to the study of the universe considered as a totality. So there were some initial worries after Einstein's, in the decade following Einstein's paper, metaphysical and epistemological worries raised by people like Milton Munitz and other people, but those worries mostly died down, and Einstein's conception took hold. Nowadays, cosmology is mostly the study of, cosmology as it's practiced today is mostly the study of totalities. Cosmologists have perfectly well-defined ways of giving content to claims about totality. So to a modern cosmologist, a totality is represented by an exact solution to the field's equations of general relativity. This is what those solutions look like, where M is a space-time manifold, GAB is a metric tensor, which represents gravitational and geometric structure of the space-time, and TAB is a stress-energy tensor, which encodes the contribution of matter. As mathematical objects, these are perfectly well-defined, and the physics of the world described by those mathematical objects present no special problems because they represent totalities. So what should we say here? How do we reconcile these two sort of apparently opposing lines of thought? One that says making a claim about the total state or the total energy of the universe is like making a claim about the total enrollment in an unrestricted class. You haven't said anything when you make such a claim that I can translate onto a definite condition on the contents of some specifiable volume of space-time. You haven't said anything definite enough that there's some particular thing or set of things that could happen that would count as settling it. And one that says it makes perfect sense to talk about the universe as a completed totality. Here are some explicit, well-defined models of totalities. When I tell you that the total state of the universe is, and I give you a Hamiltonian, I mean specifically that this is what it looks like. How do we reconcile those two things? I think the first thing to say is that we can certainly introduce models that represent explicitly specified totalities, as we do when we write down a Hamiltonian or explore solutions to the field equations. And when we are given a totality as a totality, we know how to associate truth conditions with the totality claims in those worlds. The problem is that our universe is never given as a totality, and that we can't go in the other direction. We are given one event at a time, one bit of space, time, and then another. And we could never get a Hamiltonian or a term for total energy or the total angular momentum or the total number of elephants or the total amount of anything by examining the contents of any volume of space-time, no matter how large. Even if that volume does constitute the totality of what there is, we would need to add that it did to derive the Hamiltonian. And the status of that extra fact, the fact that the contents of some specified volume of space-time constitute the totality of what there is what we're trying to understand. When And how and by what is that fact? The fact that the contents of some specified volume of space-time exhaust the totality of what there is. When is that fixed at our world? When we examine a hypothetical world by specifying its Hamiltonian, or in a quantum machine by being given its wave function, we are doing what we do in logic by helping ourselves to a fixed domain of discourse. We know that we need to do that in order to give well-defined truth conditions to universal generalizations and negative existentials. In that way, universal generalizations and negative existentials make tacit reference to totality and are well-defined only in reference to a totality. When we talk about the total state or the total energy of the universe, it's really the idea of the universe that's imaginatively supplying the boundaries that make those claims seem meaningful. We use the universe as though it were the name for a well-defined object, a large particular with determinate boundaries. And of course, cosmology furnishes us with images to draw on and giving imaginative content to its total state or its total energy. Is when we have some well-specified object, of course we can identify the total state or the total energy of that object. The question is not whether these images or the exact solutions to field equations represented by these images are well defined, and it's not whether there's a fact about the total state of the universe as they represent. Right? The question is whether there is a well-defined object already in existence, our universe, that those solutions are representations of. The total state of an imagined universe presented as complete is perfectly well defined, but the total state of an incomplete universe is not. It's not determined by anything that's already in place at any causal point, at any point in the causal history of that universe. And our universe is incomplete. So what's the right thing to say here? I think the universe as we know it, the universe as we encounter it, is open-ended and ongoing. We can wait as long as we like, fixing our own causal past and the causal pasts of all our friends and all of our families, and even in a deterministic context, the total state of the universe at some past time, and any of the global topological features that we could translate into information about its total state. For example, whether there are Cauchy surfaces and which particular surfaces are Cauchy, whether space is finite, whether it's whole free. All of those will remain precisely as open as the future. All that there is at any given moment is a developing causal order with no boundaries along the sides and a future that's neither fixed nor known. So totality is in that sense, in that precise and literal sense, never achieved, not achieved at any point within the timeline of the history it describes. We can, however, introduce a perspective from which totality facts, properties of properties of the universe as a totality, are determinate by just using a kind of formal trick that's familiar in physics. We imagine a retrospective perspective, looking back from a point at future infinity, after all is said and done. So we think, and I think this gets the content of those claims, right? At the end of the day, when all of the opportunities for extending our universe have been resolved and a full and final accounting can be made, at that point there is a well-defined totality and features of our universe, whether space is finite, which of any of these past spatial surfaces completely bisect the space-time, and so on. Then they become well-defined. Then there will be a fact about the total state of our universe in the past, because only then will our universe become well-defined. Only then will it be settled where its boundaries lie. And this is extremely counterintuitive, because you think, surely the facts along some early Cauchy surface were fixed long ago. And that's correct. But that surface is Cauchy, is not fixed until the end of time, until all sort of, until you can identify a surface that's crossed at exactly once by every time-like curve inextendable time-like curve in the space-time. Okay. So here's an analogy. So you know that sort of romantic comedy meme that where a young man kisses a woman and he says, "This is my first kiss." Okay. So even if that was his last first kiss, and even though that kiss itself might have been performed long ago, say when he was 30, the fact that it is his first kiss is never settled, so long as there remain opportunities for more kisses. In that sense, the phrase, "my first kiss," doesn't have a well-defined reference while his life is ongoing, until he's exhausted all opportunities for more first kisses. Just so, for all of the global features of our universe, they're not fixed until the boundaries are drawn, until the universe is closed. And indeed, I think we can use the paradox of predictability, that little sort of puzzle that I started with, as a kind of master argument that shows that totality outruns any attempt to specify it in advance. It will work against any attempt to give an explicit specification of totality in advance, either by listing events or by specifying a Hamiltonian and a set of laws, or by writing down an effective procedure for determining whether some future event is included in our list, because that effectively is what was supposed to happen in the deterministic context. The Laplacian demon would have a representation of the initial state of the universe and the laws, and that should have given the Laplacian demon a way of specifying for any event whether or not it was included in totality. Right? But here's how the paradox of predictability can be used as an underminer for any such claim to kind of fully prescribe in an inclusive way what totality includes. You tell me totality is everything that follows from this, either everything that follows nomologically or by some computational finite effective procedure. Right? And I say, oh really? Does it entail that I'm going to raise my hand in a second? Or what does it say about the output of this counter-predictive procedure? Right? And as soon as you've taken the time to work out your answer, then I show that you were mistaken. The possibility of undermining any attempt to fix its total state or any of the global features of our universe that pertain to it specifically as a totality and would be nomologically sufficient to determine its future in a deterministic context in advance seems to be built in to the causal structure of the universe, and also entirely consistent with determinism. So I'll leave you to decide what you think about this point at future infinity. I imagine that some people will think it's a convenient fiction, but doesn't describe anything physically real. But others will think it makes perfectly good sense, and if it's formally well-defined and it gives content to the idea of physical totality, what more could you want? I think it does get the content of totality statements and the logic of their relationship to events kind of as they're going on in the kind of ongoing causal order right. And if I have another moment, do I have 2 more minutes, maybe less? I'd like to end by connecting all of this to another issue. So if you look at the philosophical wars about time, it's a sort of battleground between 2 sides. There's the friends of becoming on the one side and the block universe enthusiasts on the other. So friends of becoming are people who warm to the idea that the universe is open-ended and ongoing, that its future is not fixed by its past, that it never, at no point in time, forms a completed totality. Block universe enthusiasts insist that there is no becoming. What there is, they say, is a fixed 4-dimensional block of events that simply comes into view in stages for creatures like us with a kind of restricted temporal horizon. And I mean, many people have said, and I think that there's one mistake that friends of becoming make, at least sometimes, when they say things like there's no change or flow in the block universe, it's just a fixed 4-dimensional grid of events. And the mistake that they make is that sort of looking down at a low-dimensional representation of time, and then instead of realizing that change and flow are represented in the content of the image, and then judging from the perspective of the supertime in which the whole thing is embedded and saying things like the image isn't changing. So change and flow are represented in the content of the image, not as features of the image. And this is what is meant sometimes when people say look, the four-dimensional representation is an image of change, not a changing image. I think that's at least sometimes what's going on. I now think that there's something just as bad on the other side, something much more insidious and harder to diagnose. It's not just that the images that we create when we sort of write down these sort of low-dimensional representations in time are static, is that they have boundaries. I mean, they're presented as complete. Whether we portray it as the block universes or the images that come from cosmology, as soon as we portray the universe as a well-defined totality, we've suppressed the contingency in its development. We imagine that space-time is like a sort of crossword puzzle with definite boundaries. We are given a certain number of spaces in a particular arrangement, and we get to just fill in the letters. Instead of sort of recognizing that we construct the puzzle by acting as we do, right? Together with all of the other parts of nature acting as they do. That is, the boundaries emerge from the action, the ongoing causal action on the ground. And I think that in philosophy, if we just simply banish the block universe, or that sort of bird's eye perspective outside of space and time, right, that looks down at the universe as a well-defined totality, and learn to think of it actually, that the content of totality statements, or the content of claims about our universe, from the point of view of the developing causal order, should be located sort of at future infinity. That's when the universe is complete, and that's when these sort of global futures become well-defined. And I wonder if that would, in some ways, at least imaginatively, diffuse the time wars. So people, friends of becoming, could sort of tolerate the deflationary eternalism that says, look, the four-dimensional view of time is a sort of benign representational transformation that preserves passage, flow, and change, and the openness of the future. But the universe, the block, is only ever as determinate as our own causal past. But it would also give us a formally well-defined meaning to talk about the universe as a totality, and it would capture the idea that totality is what will have been when all is said and done.